All right, the first couple of sections are real exciting for people who've been around for a long time because it's a review of basics. For the newbies, it might be real interesting. So don't be afraid if I'm going through something and not explaining it to you, ask. As Mark says, many times we'll hit the same thing 3 or 4 times and we build on what we get. So if you don't understand it the first time, hopefully by the 3rd time you will. Real simple. What's current? What's voltage?
Potential difference.
The pressure is potential difference. Basically, you have an electron moving around someplace. If it's a positive charge, it attracts the electrons. If it's a negative charge, it repels the electrons. Very, very basic. So how do we produce electrical charges? Got one up here already. Chemical, batteries. None of the vehicles will work without batteries, right? And there is one electric bike out there that's all electric. Sitting in the parking lot. That's what Mark drives. Okay. So, the lead acid battery is the most common, but they're coming up with all sorts of exotic materials now. Battery, right? Got to have a battery for it to work. How else can you make electricity? You'd be surprised how few ways there are. Mechanical. So how is the mechanical done? There's more than one way, but just 1 or 2.
Turbines.
Turbines. What type of turbines?
Wind and water.
Wind and water. Anyone go out to Hoover Dam? If you haven't been to Hoover Dam, it's definitely worth a trip. It's just amazing in how that works. But the wind, and if you drive a little bit to the west of here, I haven't driven to the east, drive a little to the west of here, you'll see wind turbines all over the place. Okay? How else can you do it? I heard someone say it. Solar. And that's basically the only ways you can make electricity. Either chemically, mechanically, or by solar. Right? There's really no other way. Okay, what's a conductor? Things that electrons can flow through. Okay, now we come up here. A conductor has a whole bunch of free electrons. Now, as an engineer, I have never had to measure how many free electrons are in something. Okay, but we know real quickly what's a good conductor? A metal. What's the best conductor around at room temperature? Gold. Notice I added at room temperature. You know why I added at room temperature? Superconductors. The goal is to have a room temperature superconductor. They're getting close. If they could do that, it'd be great. There actually is, and I have seen it at the Smithsonian, a superconductor coil, which basically they had a battery. They threw a circuit so that this coil of wire was connected to the battery. They opened the circuit, and it was superconducting, and that charge went around and around and around and around. When I went there, it had been 4 months. It had been in that. No resistance. It was not at room temperature. It was cold. I think it was liquid nitrogen they had it in. And they were measuring the charge, and just the measuring the charge was enough to eventually sap it off. But it went for years. So, how about poor conductors? What's a poor conductor? What do we call them? Insulator. So give me an example of an insulator. Rubber. Most common one out there is rubber. Okay. Air is an insulator. Glass, wood, all insulators. Okay. Ask you about current. What is current? Flow of electrons. Okay. Through conductors, how we normally get a flow of electrons. Okay. But it could be through anything. What do you call a flow of electrons through the air? Lightning. Yeah. Okay. So current is the flow of electrons. If you look at a conductor and you put a imaginary plane in there, and you're going to look at how many electrons move through there over 1 second, and you get 6.28 times 10 to the 18th electrons. That's a lot of electrons. Real quick question. Do you understand scientific notation? When I say 10 to the 18th, it's 1 with 18 zeros after it. Okay? Because we have the group, I want to make sure. So if I say something and you're not sure, don't hesitate asking. I don't care how basic it is. That's what this course starts out with. Real basic, and it gets tougher quick. Okay? So if you have 6.28 times 10 to the 18th in 1 second, that's 1 amp of current. So an amp of current is a lot of electrons. You know, the charge of the electron is very, very small. So when we talk about the flow of current, we're really talking about a flow of a charge. Okay. Now, convention is different from what really happens. Current flows from positive to minus. Okay. You know why it flows from positive to minus? Who's the history major? Ben Franklin. He goofed. He had a 50-50 chance. He blew it. You will see some textbooks showing it the other way around. Okay? Why? Because the instructors are stubborn old men. Okay? Just understand, whatever the convention is, just stick to the same convention. It really doesn't make a difference. And we can get into real good things because it's really not the electrons moving, it's the holes moving. If that doesn't give you a headache, I'll talk about some more stuff, but don't have to worry about that. So, you know, the accepted method of illustrating the current flows from positive to negative, okay? It really makes no difference. So long as you stick to it. It only makes a difference when you flip from one to the other. It gets confusing. Questions? What's opposition to current flow? Resistance. So what's resistance? Opposition to current flow. Well, what is it? Where do you see it? Everyone's tired.
There's heat.
It's heat. Most resistance is heat. Anytime you have something that slows down the current, the electron flow, if I can use that convention, as the electrons are moving, they bump into something and they don't flow smoothly. That's called resistance. Where is resistance? Everywhere. We talked about superconducting, and that has almost, it's as close to zero resistance as you can get. It's 0.00000000001 ohms. Very, very little. Most everything has a resistance. And when we talked about good conductors and poor conductors, gold has less resistance than silver, has less resistance than copper, has less resistance than aluminum, has less resistance, and on and on and on. but there is a resistance there. So, how do we make a resistor? Anyone know? You intentionally put something to slow down the flow of electrons. Okay. Most of the resistors are carbon, Some are wire wound, where they run a lot of wire in there and they take the diameter down, which slows things down. So the symbol is the omega symbol. I don't know if you've seen them before. And it's called an ohm, O-H-M. And on the schematic, you get that funny squiggly line. Okay? And we'll use that a lot. So 1 volt flowing through a conductor with a current of 1 ampere is 1 ohm. Gotta get you guys going. All right. We're going to start moving a little more now. It's a little physics. No physics in people here. Chemistry might work. The electrostatic force. That's really what's causing the electrons to flow. It's physics now. So, that electrons flowing through a conductor is an electromagnetic force, EMF. Yeah, do any of you guys call it EMF, electromagnetic force? Probably not. You'll call it voltage. You'll see some textbooks where they'll call it, instead of V, they'll call it E. You ever see that, where the battery is listed as E? In here you'll see it sometimes. That's going back to the electromagnetic force. That's where it comes out of. I've had a couple of teachers many years ago who didn't like the V because it wasn't clear. The E was a lot clearer, they said. You know, if the instructor wants something, you know the correct response, right? Give it to him. Exactly. Yes, sir. Okay. So, electromagnetic force required to cause 1 ampere of current to flow through a conductor with a resistance of 1 ohm is 1 volt. Okay. Voltage is also called the difference of potential or just potential. A lot of this goes back because this stuff can be equated to mechanical engineering. This works just like mechanical engineering, and we'll talk about it a couple of times as we go through here. So if you're a mechanical engineer, just think about the water flowing through a pipe and you're putting a restriction in the pipe. Okay. Or you have a reservoir, and that's your battery or your voltage source. There is no AC in the mechanical field because you don't get the water going back and forth fast enough to do anything. But you can equate it, and I had a mechanical engineer who could not do this at all, and he said one day he just said, "Oh, what? That's a reservoir. That's a pipe. Okay, whatever works. Don't be afraid." Now, there's 2 types of voltage that we deal with. There's a lot more, but there's 2 main types: DC and AC. What's a DC voltage? Direct. What does that mean? Electrons flow one way. What's an alternating current? Flow both directions at the same time? They alternate. Now, one thing about AC, if it's AC, it's positive half or part of the cycle and negative part of the cycle. It has to go through 0. We'll talk about that later on, but when you start doing signal analysis, that makes a difference, because in describing the waveforms, you have to learn how to describe them correctly. So now we're going to learn the most basic equation, the most useful equation in all of electrical engineering. Ohm's Law. The voltage applied across the resistance causes the current to flow. So you have a voltage, you have a current flow, you have a resistance. And there's a very simple relationship. V equals IR, where V is the voltage, I is the current, and R is the resistance. So, from looking at that, if resistance stays the same, what happens if the voltage increases to the current? Okay. There's a very simple relationship. You can put your numbers in there and they work all the time. As you go through circuit analysis, this is one of the most basic things you want, and you try to reduce your circuit to that because you can visualize this as you work with it long enough. So V equals IR, E equals IR is the other way you'll see that written. That's the most common way, actually. E equals IR, that's the way Ohms Law wrote it. But we use V. When did it become V? Probably around the 1930s or 40s, when batteries became really big. If you think about this, since we have some history people in here, electricity wasn't big until Edison and Tesla started making it big. Go all the way back to Ben Franklin. There was a lot of experiments with batteries and charges. Ben Franklin with the kite, which probably was not true. Has he actually done that experiment? They've tried it. It kills people. Okay? Think about it for a second. You're out in the rain. In the rain. You have a kite. You have a cord. What's the cord made out of? Cotton. Cotton cord with a key up into a lightning storm. The lightning hits the key, because it's metal will attract it. Where's the charge going to go? Because it has to get to ground. Where's it going to go? Right down that string, right through your hand, right through your body into the ground. Okay, so he was right, but Ben Franklin was more of a theoretical guy as well as practical. So they really think he did some observations. And he would get the Leyden jar and charge it up. And you can charge it up without using lightning. And they would do experiments. Then, around the time of Edison and Tesla, they were doing a whole lot of work. And Tesla got the short side of the stick because Edison was a DC guy. I grew up in New York City. Do you know New York was first wired for DC? You know what the problem of having DC for your power lines are? Transmission distance. Yeah. The New York City subway has its own generating systems. It's all DC, 600 volts. Lower Manhattan has all been converted over, but parts of Brooklyn, there was a couple of hotels that they were all DC in the hotel. Now, the outlets in the room were, but the power that ran everything in the hotel were DC. All Edison's. Tesla was the one who came up with AC and made it more practical. So that's voltage at that point is about when voltage, although E is still common.
Why is there a difference in transmission
Distance?
Yeah.
We'll talk about that more later on, but basically it has to do with what they can do to the power and the current. Remember I said if your resistance stays the same and we increase the voltage, the current decreases. Okay. Well, if the current decreases, the losses decrease over distance. But we talk about that a couple times. Good question. All right, series and parallel. You familiar with series and parallel? Okay, here is two circuits. We have 1.5 volts, 1.5 volts, 1.5 volts, 1.5 volts in series. Ends up, you add them up. Voltage is nice. You just add them, you get 6 volts. We show it this way as a battery. Now, usually it's just too long and too short. They're being convention. Most times it's just a 2 and 2. Here's parallel. Okay, you have this plus this plus this plus this, and this plus this plus this plus this. Well, this plus this plus this plus this, their 1.5 volt is what? This plus this plus this plus this is what? 6 volts. Draw them this way. The potential from here to here is still 6 volts. It hasn't changed because these are in parallel. So what does that tell you about the current capacity? Higher, it's doubled. Okay. Same thing. If I break this wire here, what's the voltage out here? 0. If I break this wire here, what's the voltage out here? 6 volts. Okay. So if you're doing circuitry and circuitry analysis, you need to understand that. And we're going to go through a whole bunch of other components, and they all work differently. Okay. There was a time when I was building up circuit boards, and I was building them up all the time, and we had a box with resistors in it. And I would pick out a resistor, I'd look at it, and I knew what all the color codes were. Don't ask me what the color codes are anymore. When I got to find them, I got to look up at the chart. In the electronics lab, if you have a good electronics lab, they're going to have a chart up there with a resistor with all of the color codes on there. Right? So I'm not going to try to make you understand what they all are. But when you look at the bands, this is telling you the resistance. The first critical number, the second critical number, the multiplier, and then the tolerance. Thank you. If you saw a fifth band here, do you know what the fifth band is? If you work with aircraft, normally they do. Missiles especially. That's the failure rate. I've seen them occasionally, but not very often. But when you look at them, you look red, green, yellow tells you it's 2, 5, 10,000. And then it's plus or minus 10%, which means that can be anywhere from 2750K to 225K. So when you're doing a circuit board and you say I need a 250,000 ohm resistor, and you reach into the box to pull them out with a 10% tolerance, you can get anything in that whole range. So just be aware of that.
I remember back when we had to, the Navy had code to memorize that.
Oh yeah, they want everyone to memorize it.
Yeah, and you know what? Unfortunately, it's stuff that it was like bad boys race. Our young girls behind picture garden walls get started now. It was like black, brown, red. I mean, you like literally like
Constantly.
Still that in here. And I used to
I was going through it and I'm going, man, I hated memorizing that. And we always had in the lab, even when I was a young engineer, we always had in the lab the chart up on the wall. It's up on the wall. Why do I got to memorize it? You know?
we didn't have that chart.
You didn't. If you don't have that chart, you call most of the manufacturers. They'll ship it to you at no cost. They'll be happy because I have an ad down at the bottom telling you buy your resistors from Newark Electronics. Whatever. The last thing is the schematic symbol at the bottom here. It's just that squiggly line. Questions? Okay, here's two circuits. They're very simple. You have a voltage, you have a current flowing, and you have resistance. Voltage is 300 volts, resistance 150. What's the current? I equals V over R. 300 divided by 150 is 2 amps. Simple, easy. Now we have three resistors. 100, 150, 50. What's the resistance? Real tough. 100 plus 150 plus 50, 300. So what's the current flowing there? Current equals V over R total. That's the total R. 300 divided by 300 equals 1. We did the math so that engineers can do it without a calculator. Okay? Resisted circuits are the easiest, which is why people like to reduce things down as much as possible to the resistance. Questions? Now, in series circuits, you just plain add the resistance to get the total resistance. Okay? We've gone through these. They're pretty simple to do, right? Here's another one. If we know the current flow, we now can figure out the voltage drop across each resistor, right? So the total voltage is 300 here. What's the current? 1 amp. So what's the voltage drop across here? 1 amp times 100 ohms is 1 volt. Okay? 100 volts, sorry. Over here, what would it be? 1 amp, 150. And down here, 50. That's how you start doing your circuit analysis. Okay? Question. Any questions on it? I'm glad, because this is the easy stuff. Okay, how about power? What's power? The ability to do work. I like that. Okay. So if we have the same circuit, how much power is consumed by each of those resistors? How would we figure it out? Power is equal to voltage times the current. So the first one, you have 100 volts and 1 amp, you have 100 watts. Total would be 300 watts. They don't come out this easy in the real world, but you know. We do it that way just to make it easy for you to get the concepts. All right? And that's power consumption is an important thing that everything you're doing, even more so now than years gone by. But power is real important. All right, now let's go a little more complicated. We're going to go to a parallel circuit. So how do we calculate the resistance in there? What's the potential from here to here? 10 volts. What's the resistance? What's the current flow? The current flow through here is 1 amp. What's the current flow from here? 1 plus 1 plus 1. 3 amps. Okay? What's a capacitor? Storage tank, okay. DC circuits, it's a storage tank. An AC circuit, that's something else. What? No, it's not a converter, it's a filter. An AC circuit, the capacitor keeps out the DC. You filter out the DC, if you will. But a capacitor is basically a storage device in a DC circuit. You have 2 plates, you have something in between them, and as the current goes in, the one plate charges up, and you get a potential difference between them. So, you know what this symbol is up here? It's a switch. Okay. The other circuits we showed you are not real circuits. You don't have any circuit without a switch. All circuits have some sort of switch, so in the real world. So you throw this switch down, the electrons come from the top plate, and they end up on the bottom plate. Okay? And so you end up with a potential across those two. Capacitance is, the symbol for capacitance is Q, which is coulombs. It's the charge. Why is it a Q? I don't know. Never asked that question. Okay. But it's the amount of electricity which can be held in an electric field between the plates. And it's a coulomb is equal to the farad, the capacitance, times the voltage. You have different materials in between the plates. It changes the capacitance of that circuit, or that component. In this example, you have 2 plates with an air gap. You have a 1 farad capacitance. You put polyethylene in between, you get 2.3 farads. Okay. The other thing is, when I started, this was the symbol for capacitance in all electrical circuits. It's now this symbol, this curved area. Do you know why they changed it? Yeah, but not really. There's other ways to do it. Engineers are lazy, and some engineers would draw it like that. What does that look like? Little cell battery. Okay? So, there was confusion. So the International Standards Organization says we're going to draw it that way. You still will see it this way, especially with the Navy. A lot of the stuff in the Navy still has it that way. Just don't be upset if you see that. So what happens when we have capacitors in parallel? You add up the capacitance. So here, to figure out the capacitance here, it's 1 plus 2 plus 3 microfarads. Are you familiar with the micro symbol? Okay. That's 10 to the minus 6th. So when you add them all up, it's 6. So capacitors in parallel are easy to add. If they're in series, it's 1 over 1 over the number. Okay? So now you have to do a little math. So here, if we add these up again in series, you'd have 1 divided by 1 over 1 plus 1 over 2 plus 1 over 3 Okay. Remember the math, in order to add fractions, you have to have the same denominator? Remember that? Okay. It's okay if you don't, because I've been working with my daughter and she forgot all about that. It's amazing. And she's 33 years old, so don't feel bad. She forgot. So the common number here would be 6. So it's 6 over 6 plus 3 over 6 plus 2 over 6, 1 over that. When you add that all up, it's 6 over 11. And 6 over 11 is 0.55 microfarads. Okay? That's only because they were all in microfarads. If one of these was in farads, you'd have to convert it into microfarads. It just makes the number larger. Or if it was in picofarads, it would make the number smaller.